Welcome to the second series on using rigorous methods when analyzing long transmission lines. As you know, the last time, we have been able to derive the formula for the sending end voltage Vs and the sending end currents Is respectively. In today's series, we will use the formula derived to solve a typical long transmission lines using rigorous method. Without any further ado, let's get started.
Now we can solve the following question using the formula that we derived in the previous series. So, a three-phase transmission line 320 kilometers long has the following constants. Resistance per phase per kilometer is equal to 0.19 ohms. Reactance per phase per kilometer is equal to 0.32 ohms, and shunt admittance per phase per kilometer is equal to 2.39 times 10 raised to power minus 6 mho. Calculate by rigorous method the sending end voltage and the sending end current when the line is delivering a load of 480 megawatts at 0.86 power factor lagging when the receiving end voltage is kept constant at 330 kilovolts.
We can begin now by solving the following. Total resistance per phase per kilometer, that is 0.19 times 320, this will equal to 60.8 ohms. Likewise for reactance 2, that is the total reactance XL is 0.32 times 320 is equal to 102.4 ohms, and finally for shunt admittance 2, which is the total shunt admittance, will equal to 2.39 times 10 raised to power minus 6 times 320 will equal to 7.64 times 10 raised to power minus 4 mho.
Having calculated for the total resistance, reactance, and shunt of the line in a span of 320 kilometers, then the series impedance can easily be obtained. That is because impedance Z is the combination of resistance and reactance. Impedance is equal to resistance plus JXL. That is 60 plus J 102.4, and when converted from rectangular form to polar form, the impedance of the line will be 118.68 at an angle of 59.63 degrees. In the same vein too, the shunt of the admittance of the line can easily be written as 7.64 times 10 raised to power minus 4 at an angle 90 degrees mho.
Again, when the sending end voltage per phase is given as the sending end voltage Vs is equal to the receiving end voltage Vr multiplied by cos h square root yz plus the receiving end current Ir multiplied by square root of impedance all over admittance multiplied by sin h square root impedance and admittance. Now, before we can slot our value in, we will need to calculate out each variable one by one. So we can slot in the value of our impedance and admittance that we have calculated out earlier in here. That is, the square root's impedance multiplied by admittance will be equal to square open bracket 118.68 at an angle 59.63 degrees close bracket multiplied by open bracket 7.64 times 10 raised to power minus 4 at an angle of 90 degrees close bracket. The resultant of this will be 0.30117 at an angle of 74.81 degrees.
Impedance multiplied by admittance can be calculated out too. That is 118.68 at an angle of 59.63 degrees multiplied by 7.64 times 10 raised to power minus 4 at an angle of 90 degrees. This is equal to 9.067 times 10 raised to power minus 2 at an angle of 149.63 degrees. Likewise, impedance square and admittance square can be calculated out too. So when we square this here, the impedance square and admittance square will be 8.221 times 10 raised to power minus 3 at an angle of 299.26 degrees.
Square root of impedance all over admittance is equal to the square root of 118.68 at an angle of 59.63 degrees, all over 7.64 times 10 raised to power minus 4 at an angle of 90 degrees. This will equal to 394.13 at an angle of minus 15.18 degrees. Also, the square root of admittance all over impedance will be equal to the square root of 7.64 times 10 raised to power minus 4 at an angle of 90 degrees, all over 118.68 at an angle of 59.63 degrees. This will equal to 2.53 times 10 raised to power minus 3 at an angle of 15.18 degrees.
Calculating the value for cos h square root admittance multiplied by impedance can now be easily resolved which is equal to 1 plus admittance multiplied by impedance all over 2 plus admittance square multiplied by impedance square all over 24. So when we slot our value in here, we will have this here. Again, in order to add both ends here, we will need to convert from polar form to rectangular form. When converted, we will have this here. So the addition of all these complex numbers in the rectangular form here will be 0.961 plus j 2.29 times 10 raised to power minus 2, and when converted back from rectangular form to polar form, our answer will be cos h square root admittance multiplied by impedance will equal to 0.9612 at an angle of 1.365 degrees.
Sin h, on the other hand, can also be calculated out too, so we will have square root, open bracket admittance multiplied by impedance plus admittance multiplied by impedance close brackets raised to power 3 all over 2 and further all over 6. Now when we slot our values in here, we will be having these. When the right side is further simplified, we will be having these here, and further divided by 6 here. The right side will be 1.24 times 10 raised to power minus 4 at an angle of 299.26 degrees. Again, in order to add them both, we will need to convert from rectangular form to polar form. Now when converted, we will have this here. Now we can add both. When added, our answer will be 0.078 plus j 0.289, and when finally converted back to polar form, our answer will be 0.299 at an angle of 74.89 degrees.
Before we can go ahead, we need to calculate out the receiving end parameters for both the receiving end voltage and current. So for the receiving end voltage VR, it will be the line voltage all over root 3, that is 330 kV divided by root 3. This will equal to 190,525.588 volts. Likewise, the receiving end current IR will equal to the power delivered all over root 3 multiplied by the receiving end voltage multiplied by power factor. So, 480 megawatts all over root 3 multiplied by 330 kV multiplied by 0.86. This will equal to 976.49 amperes.
Now we can substitute and solve for the sending end voltage. So when substituted, we will have these here. And before we can add for end to end here, we will need to multiply like terms at both ends. After multiplying both ends, we will have these here. Now that we have multiplied both ends and we have our resultant values, we will need to add them both. However, in order to be able to continue by adding both end, we will need to convert from polar form to rectangular form. When converted here, we will have these here, and when added, our answer will be 241,081.57 plus j 103,722.28 volts. Again, we will need to convert from rectangular form back to polar form. When converted, our answer will be 262,447.394 volts at an angle of 23.279 degrees.
Also, the sending end current IS can also be calculated out too, so when we slot our values in, we will have these here. Again, we can multiply the like terms at both ends here, which will result in these here. Again here too. In order to add both ends here, we will need to convert both ends from polar form to rectangular form. When converted here, we will have this here, which is 938.335 plus j 22.35, and when converted from rectangular form to polar form here, our sending end current will be 952.814 amperes at an angle of 10.06 degrees. Now that we have known the current that will flow at both ends of the lines, that is at the sending end IS and the receiving end IR, then we can say that these transmission lines will be a bundled conductor circuit transmission line.
Again, it is worth noting that multiple conductors per phase are employed in transmission lines primarily to reduce corona discharge, improve transmission efficiency, and increase power transfer capacity.
Overall, to sum it up, with an increase in the effective radius of the line and a decrease in the electric field gradient. Thus, it helps to prevent overheating of the transmission line. And that is it for this series. In the coming series, we will be using ABCD parameters to solve problems related to long transmission lines. So until then, peace.